Hello, this is another video based on the book Introduction to Probability by Blitzstein and Huang, which you can find on the internet or even download. This video is on combinatorics. That's the second part of a video on combinatorics. And here we have a birthday problem. Let's suppose we have k people in a room. And let's assume that people are equally likely to be born throughout the year. And let's assume it's not a leap year. And let's assume that all these people's birthdays are independent of each other. So, for example, people will not be twins, because if they're twins, they'll have either the same birthday or perhaps consecutive birthdays. So the question is, what is the probability that at least one pair of people in the group have, maybe we should say has the same birthday? So we have lots of ways there are lots of ways that these people could have birthdays spread throughout the year. Given a normal year, there are 365 days. We have k people. And so there are this many ways that people's birthdays could be spread out evenly and independently through a year of normal length. Now, if we want people's birthdays to all be different, then we're going to have to think about how many slots we have for the first person's birthday. Not that the order really matters, we have to start somewhere. So when we're starting to make a list of who has birthdays when, there are 365 days in which our first person can have a birthday without repeating anybody's birthday. Then we get to the next person, 1 day is already used up. We get to the next person, 2 days are used up, and so on. And so this would be more generally, we'll get to 365 minus k plus 1, which you will recognize when you multiply all that out as 365 factorial over 365 minus k factorial. Now you'll notice that we now have to assume that k is less than or equal to 365. Clearly, if we have more than 365 people, and this is, we're not worrying about leap years, then we will have to have some repetition. We could generalize the problem to include leap years a little bit, but let's not work that hard. So here we have, forgetting about leap years, we have how many ways there are for k people to have their birthdays spread throughout the year without any repetition, while over here we allowed repetition with 365 to the k. And so our probability will be equal to the ratio of these two expressions, so 365 factorial over 365 minus k factorial. So this is one expression. And then we need to divide by the possibilities if we allow birthdays to be reused. Now we could use a negative exponent, but hey, I said a ratio. So let's have a positive exponent and a denominator instead. And of course, k has to be less than or equal to 365. Otherwise, there will be 0 days for the 366th person to be born while getting a unique birthday. So there we go. There's the birthday problem. Now we want to consider sampling of a jar that has a bunch of balls in it. Call it a jar. Sometimes we call it an urn. It could be a bag. It doesn't really matter. These balls might be like billiard balls. Those are some of the most familiar balls that come labeled with numbers 1, 2, 3, and so on, at least up to a while. So we'll have to distinguish, as we briefly saw earlier, between sampling with replacement and sampling without replacement. So if we sample with replacement, then that means after we take a ball out, we put it back. So that would be like allowing people to have the same birthday, in the context of the birthday problem. So if we sample with replacement, as the problem says, then we have n possible balls that we could draw, and we do this sampling k times, and so we have n to the k ways to get a sample of size k, to draw n balls in sequence. Now, we can draw what we mean by sampling with replacement. So we've got a ball here. Here's number 1, here's number 2, here's number 3, and so on. We take a ball out for our experiment, but then we put it back in when we're done. We are replacing, aren't we? Okay, and so that's how we get n to the kth power, because we have n possibilities, and then with the ball replaced, we have n possibilities, and we have n possibilities, and so on, until ultimately we have n k of these. So we'll have a k ball sample. Now, what if we change the problem and we say no replacement? That's kind of like our numerator from the birthday problem, where we said we wanted everyone to have a distinct birthday. So now, if we have our slots, we can have n possibilities for the ball that's drawn. But since we don't put the ball back, there are only n minus 1 balls in the jar. And then we'll have n minus 2 after we've already removed 2, and so on. And so we'll wind up with n minus k plus 1, because we want to make sure that we have k, and this is one of those unpleasant things about endpoints. We take the difference and we get what, k minus 1, but remember I have to count both endpoints. Since we're not interested in the difference, we're in the total number, interested in the total number of balls that have been sampled. And this looks again like it will fit our permutation formula. So we have n factorial over n minus k factorial So recall, of course, I did say we are changing the problem. So that was the second problem when we had no replacement. Okay, next we are asking about rolling 2 fair dice and thinking about which rolls are the most important. If you play games like Monopoly, then this will be something useful to know. We have two fair dice, which is more likely a sum of 11 or a sum of 12. So evidently Leibniz thought a lot in terms of his philosophy, which said there weren't indistinguishable things, basically. But that isn't our experience with dice, where we can clearly tell dice apart because of, for example, their spatial location, if nothing else. They could be different colors or something like that. So if we roll two fair dice, there are six possibilities for one die and six possibilities for the other die. So that gives us 6 squared, which is 36. Now the values kind of in the middle for the sum, like uh, 7 will tend to be favorites, while ones at the extremes, like 2 or 12, will be the least likely, because 2 we can get as 1 plus 1, 12 we can get as 6 plus 6, 3 we can get as 1 plus 2, or 2 plus 1, and these are distinct. 11 we can get as 6 plus 5, or as 5 plus 6. So we have two of these ways to get an 11, one way to get a 12, one way to get a 2, two ways to get a 3, and then there are more and more as you go up towards the middle and hit 7, and then they shrink again. So if we want to show not every case, but like the most probable one, 7, if you get 1 plus 6, you get 2 plus 5, you can get 3 plus 4, you can get 4 plus 3, which is different because the dice are distinguishable. You can get 5 plus 2, you can get 6 plus 1. And so we've got 1, 2, 3, 4, 5, 6 ways to roll a 7. So Leibniz actually claimed that there were not two objects that were exactly alike. Like if you had any two leaves, they would not be just alike. And maybe if you collect a lot of leaves and look at them, you could find some difference. But for Leibniz, that wasn't just something that you learned by going out and checking. You could only falsify it that way, I suppose. But it's something you're supposed to know in advance. Well, maybe people don't know quite as much in advance as might be tempting on some occasions. Okay, so club officers. In a club with n people, we can, let's suppose we are choosing 3 distinct leaders. There are n possibilities to be the president and n minus 1 possibilities to be the vice president after you've picked a president. And then maybe you have a treasurer, probably the third office you'll have. Then there will be this many ways that you could have a president, a vice president, and a treasurer. If we had a secretary, then you could add another factor, then minus 3, and so on. But you'll notice we don't do any sort of division. It's not that we're in love with the permutation formula or the combination formula. Those are just two fairly well-known things that come up. So if these are distinct offices, then the order in which we choose them matters. So if you have person A, person B, and person C as president, vice president, and treasurer respectively, then with distinct offices, the order in which we write them matters. A, B, C would be different from B, C, A, and so on. Now, what if we have, instead of 3 distinct offices, we just have 3 leaders? Triumvirate, I suppose one could say. Such a thing occasionally happened in the Roman Empire. Well, in that case, we will have this many ways. Of course, we don't reuse people if we don't allow one person to hold multiple offices. So let's assume that no one can have multiple offices. So again, not n cubed, but n times n minus 1, n minus 2, and all that applies before as well. But now that they're all equal, they're just leaders, we want to divide by our overcounting. because having A, B, C be president, vice president, and treasurer, is different from having A, B, and C just be leaders. If we have only leaders, a triumvirate, then we would need to divide by 6, um, which is what? N factorial over n minus 3 factorial. So, and then another 3 factorial to divide out by the overcounting. So earlier we had n factorial over n minus 3 factorial. So again, notice it's not that we are in love with the permutation formula or the combination formula necessarily. I mean, we may get one, we may get the other, we may get something else. It just depends on the nature of the problem. So we give names to some that are sufficiently important to be memorable, but they are not all of the possibilities, as will become evident in our next example, which involves, well, first of all, choosing a 2-person committee, and after that, choosing 2-person teams. So let's consider part A. How many ways are there to choose a 2-person committee if we have 4 people to choose from? Well, we can't reuse, if you don't get a 2-person committee by putting one person on it twice, do you? That isn't a 2-person committee. So we get one person who can be our first on there, and then another one who can be our second, but there are only 3 to choose from anymore. But if it's committee membership, being the first person put on or the second has no significance at all. It's just a matter of our bookkeeping. So this is what, 4 times 3 times 2 times 1 over, well, we had 2, which is the same as 2 times 1, and then we have another 2 times 1, haven't we? So this will be 4 factorial over 2 factorial, 2 factorial, which is 4 choose 2. Now that was A, but what if we want to just break people into teams? Well, here you will notice that if we put 2 people on a committee, then we have 2 people left over. And so we were making another 2-person group at the same time, which leads us to think if we're thinking about teams, then maybe we will have done some overcounting. So now let's think about teams. And we can do a little brute force here, listing all the possibilities. So let's let our persons be A, B, C, and D. Then we could also have, so if I choose A and B, then C and D are left over, but they wind up being a team. If I choose A and C to be a team, then B and D wind up on a team. If I choose A and D to be on a team, then B and C are on a team. So notice just by I start with one person and then I pick that person as teammate, then it looks like I'm just about done. But let's see. Let's try to do a little more brute force and see what happens. BCAD, well, since being this first group here no longer means these are on the committee and these aren't, they're just a matter of teams, I see what? Do I see repetition here? Yes. I had AD and BC on teams. Here I have the same thing. So this is redundant. Now I could also try putting B and D on a team, but that will leave A and C on a team. And then I see I've already got this possibility. Also, I could try putting C and D on a team, which leaves A and B on a team. But that's the very same thing as this one here. And so we wind up having to do an extra division. So up here, I never did write the value, did I? That was equal to 6. But down here, our answer is not from the combinations or permutations formula. And then we have an extra 2 to divide by. I mean, maybe more generally we could discuss whether that should be a 2 or a 2 factorial, but in our case, is already sufficiently detailed. Oops, sorry, that's not divided by 3, it's divided by 2. So that's equal to 3. So the basic idea is if we realize we've overcounted something, then we just cancel out our overcounting. It doesn't have to get a special name like permutations or combinations. We just think about the meaning of what it is that we're doing, and then that enables us to make corrections as needed. And then we will have a problem that involves permuting letters of a word. Well, this isn't much of a word, is it? La, 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 evidently is our word here. But let's try permuting this. So we have 8 letters, but there's a lot of repetition because we've got 3 L's and 5 A's. So we could do this in 2 different ways. We might say we've got 8 choices for the first letter, 7 choices for the 6th letter, 6 choices, I'm not sure what I said, 7 choices, 7 for the second letter, 6 for the third letter, 5 for the fourth letter, and so on. So we're permuting all the letters in the word. So I don't want to stop early. However, I have some repetition. So I'm not really using the permutations formula because well, it's a trivial case, an extreme case. But then I need to divide by the fact that I am repeating the L and I'm repeating the A. So this turns out to be 8 choose 5 or 8 choose 3, keeping in mind that these are equal to each other. So again, it's not our goal to get everything to be shoehorned into a combinations or permutations formula. We think those are using our tools and then see what it is we come up with. So this is 8 times 7 times 6 over 5 factorial. I just have to cancel out. Now we get 3 factorial, which is 3 times 2 times 1. So that's 8 times 7 times 6 over 6. So this is just 56, isn't it? Okay. So it turns out to be equal to the combinations formula, interestingly. Now you can think of this alternatively as choosing where to put the 5 A's. You have 8 places to put an A, and after you put 1, you've got 7 places to put an A, and then you've got 6 places to put an A, you've got 5 places to put an A. You got 4 places to put an A. So you can do that, but then you say, wow, I've overcounted because all of these A's are the same, so you would want to divide by 5 factorial. But you could think of where to put the L's. You'd have 8 times 7 times 6 places to put the L's, but then you realize this is overcounting because these L's are all equivalent, so you divide by 3 factorial. So there are lots of different ways to think of this, but they all give the answer of 56. Now we have another question, which is similar but a bit harder. It involves the Okay, so now we want to permute the letters of the word statistics, which has a fair number of letters, and there's a certain amount of repetition. So this is going to be a more interesting problem. One thing we could do is say, well, we have 10 letters. So we've got 10 choices for the start, and then we've got 9 and so on. But there is going to be some repetition, and so that gives us 10 factorial. But there is some repetition. Notice that the letter S appears 3 times, so I'll cancel that out. Notice the letter T appears 3 times, so I'll cancel that out. I should write a 3 here, not a T. And then the I appears 2 times, and so I should cancel that out. And this turns out to be 50,400, but there's something else that we can do, and it's similar to a way that we worked the previous problem. We can try to work this into places to put the S's, and then places to put the T's, and so on. So we have, for our S placement, we would have 10 factorial over 7 factorial. That's how many ways we could place the S's. So it's 10 factorial over 7 factorial, and then we notice we've overcounted because these S's are all alike. So we get 10 factorial, 3 factorial. Now so far I have thrown in a 7 factorial because I wanted it, so I will cancel out by putting it there. Now we've also got a 3 factorial. This isn't equal yet. I'm going to make it equal eventually. We've got a 3 factorial here. Now, if I want to get this in terms of some kind of combination coefficient, then I'm going to want a 4 factorial in here. So I'll put that in because I want it, which I can do only because I'm canceling it out. Keep in mind, if I multiply by 4 factorial and divide by 4 factorial, I'm just multiplying by 1, and I can always do that for free. So that's fine. Now I've also got this 2 factorial sitting here. So that needs to be here. But this doesn't yet look like a combination binomial coefficient, does it? So I'll put another 2 factorial in here because I want it, but now I'm going to have to cancel that by putting it in the numerator. Now, if I put this in the numerator, this equation should now be true because, let's see, the 7 factorials cancel out. I've got 2 3 factorials, which I want. The 4 factorials cancel out. I've got a pair of 2 factorials canceling out, and 1 remains. But this is not yet one of those coefficients, is it? But if I put 1 factorial, then I've got what I am looking for. And you could think of this as where to put the S's, and where to, of which there are 3, and where to put the T's, given that I have placed the S's. There are now 7 possibilities left. And then we would be able to